Hi, I'm Seungyeon Seo, and in this video, I'll be presenting FlipNeRF flipped reflection rays for fusion novel view synthesis. Let's begin with the motivation behind our approach. When NeRF is trained with only a small number of views, we observe significant performance degradation. This is a critical challenge we aim to address. One key insight is that precise surface normal estimations lead to accurate depth map reconstructions. This forms the foundation of our strategy to improve NeRF's performance. Now let's introduce a novel addition to our training approach, flipped reflection rays. By incorporating these additional rays, we aim to achieve more accurate normal vector and depth map estimations. Initially, let's go over the training framework of neural radiance fields, abbreviated as NeRF. In order to effectively train NeRF, it necessitates a varied collection of images captured from various perspectives. These images are then linked with their respective camera poses. This process leads to the successful generation of high-fidelity synthesized views. Nonetheless, if NeRF is presented with a limited set of inputs, its performance and precision may be compromised due to inaccuracies in the underlying 3D geometry. To tackle this problem, we exploit a batch of flipped reflection rays as extra training resources which are derived from the original input ray directions D and estimated surface normals N hat. First, we derive a flipped reflection direction D' from D and N hat. To generate the additional training rays based on D', we need a set of imaginary ray origins located in a suitable space considering the heating point and the original input ray origins. Therefore, we place O' so that the S sample of R', whose blending weight is the highest along array, is P subscript S. Nonetheless, because the estimated normals used to calculate D' are not absolute truths but approximations, there is a worry that incorrectly computed R', which don't meet the criteria of photoconsistency, might still be employed in training. This could potentially lead to a decrease in performance while offering misleading training signals. To tackle this issue, we implement a masking approach based on the angle between N hat and minus D hat. Through this masking process, only R', which are cast toward the photoconsistent point, can be remained as we intend. Let's take a look at the FlipNeRF in more detail. First, our FlipNeRF is built upon MixNeRF, which models array with a mixture model of Laplacian distributions, utilizes a set of flipped reflection rays as additional training resources. And we propose uncertainty-aware emptiness loss. By the UE loss, we are able to regularize the blending weights adaptively. It is able to reduce floating artifacts consistently across the scenes with different structures and enables to synthesize more reliable outputs by considering uncertainty. Furthermore, motivated by previous works addressing the feature consistency, we encourage the consistency of bottleneck feature distributions between R and R', which are intermediate feature vectors, by Jensen-Shannon divergence. By our proposed BFC loss, we regulate the pair of features effectively by enhancing consistency between bottleneck features without depending on additional feature extractors. Here are the analysis of FlipNeRF. We present a comparison of masking conditions for the flipped reflection rays. Our masking strategy of filtering out the ineffective flipped reflection rays with a threshold of 90 degrees achieves the best performance among different options. With the threshold of 30 degrees and 60 degrees, the rendering quality is rather degraded since the newly generated rays are overly filtered and do not provide enough additional supervision. The table shows the effectiveness of our proposed UE loss. Compared to MixNeRF, which models array with mixture of distributions as our FlipNeRF, ours consistently achieves more reliable rendering results with much lower NLL. For the BFC loss, we compare different strategies with our proposed BFC loss with JSD. And through the ablation study, we confirm that we are able to achieve performance improvement by a large margin with our proposed losses. Here are the results of MixNeRF and our FlipNeRF. Our FlipNeRF renders the images from novel views with much fewer artifacts and more accurate depth maps than MixNeRF. Considering the standard deviation of RGB and depths, our FlipNeRF is able to estimate more reliable outputs than MixNeRF. Here are the comparisons with other baselines. Noticeably, our FlipNeRF estimates more accurate surface normals than other baselines, leading to the performance gain with better reconstructed fine details from limited input views. Thanks for your attention.